Hey students, welcome to class. Thanks for joining me and my dog Harlow. You probably hear her in the background. Maybe my dog Jazzy will pay us a visit. We'll see. If you hear lots of snorting in the background, it absolutely is one of them. Not me. So, I thought maybe you might want to learn a little bit about the law of sines today. So, we started off studying trigonometry, and we really were focused on right triangles and SOHCAHTOA, and we were targeting finding parts in right triangles, whether it be the acute angles using inverses, or the missing sides using a trig ratio like sine, cosine, or tangent. And then we moved on, and we started looking at trigonometry in terms of outside of a triangle. We looked at the unit circle and how we can extend trigonometry to outside of a right triangle. And probably the next logical step, or maybe the step that could have, I guess, been before the unit circle, was what about if we don't have a right triangle? But we do have a triangle, but not a right triangle. And we know there's these great relationships in right triangles, Pythagorean's theorem and all that. And in any right triangle, always know they have one angle that you for sure know it's a 90-degree angle. But if you have an acute triangle or an obtuse triangle, you don't have one guaranteed angle that you already know. And you don't know the set relationship between the lengths of the sides as we do with Pythagorean's theorem. So back in the day when people were kind of just first studying about triangles, they noticed this too. They said, well, these other triangles we can't treat the same way. And they knew that there was definitely a need for some way to find missing parts of them. And we've seen so many applications of triangles, we kind of know why that might be. So as they were discovering relationships between these other kinds of triangles, they discovered this thing that was eventually called the law of sines. And basically what it said is no matter what kind of triangle you have, and this could even be in a right triangle, the relationship between the sine of an angle and the side across from it, that ratio, was always equal in any given triangle. Those three ratios that compared the sine of an angle to its side across from it, in a certain triangle, those values were always the same. And the most common way we express that is like this. We would say that the sine of an angle A over its side across from it, little a, must equal the sine of angle B over its side across from it. And it also equals the sine of C over the side across from it, which is little c. Now I've seen sometimes this written with everything flipped and have the sides on top and the sine of the angles on the bottom. But in any given triangle, that could be a right triangle, obtuse triangle, whatever, if you look at the sine of an angle as it relates to the side across from it, they will always be equal in any given triangle. And we know that there's this set relationship between angles in a triangle and the side across from it. We already know that. And this is most likely something that you learned in geometry. But we're going to review that, and we're going to look at how we can find parts using the law of sines. Now, when can we use the law of sines? Because you can't just use it just any time. Specifically, the law of sines can be used to find sides and angle measures when two angles and any side, or the angle side or angle side angle condition, are given, or if you have two side lengths and an angle outside of them, which was SSA. And so that's kind of something you have to kind of go back and remember those, if you remember those similarity, or those congruence theorems, I guess I should say, in triangles. And so, that is a way to tell whether you can use the law of sines. But the way that I do it is I just look to see, in my triangle, do I have an angle side pair where I know both of, or can really easily find both of? In other words, two known values, like I know the angle and the side across from it, and I know that one pair, that means that I'll be able to use the law of sines. So like for instance in this first example, example 1, I can see that I have this, and I like to kind of loop these together. That's just something that I do to kind of help me focus on the things that go together, is I know that those two go together. I'm looking for side x, so I know that x goes with the angle across from that, which is 52 degrees. And so if I wanted to find x, I could say something like this: the sine of 34 degrees over the side across from it, which is 10, must be equal to the sine of 52 degrees over the side across from it, which is called x. Now, when we use the law of sines, we don't use all three ratios at once as stated in the actual law of sines up here, but we just take any two of those where we know three of the four things. And if we know three of the four things, we can then use the cross products like this. I could multiply these two things and multiply these two things, and I would get an equation I could solve. So what this one says is if I take 10 and multiply it by the sine of 52 degrees, it will equal x times the sine of 34. And now all I have to do to get x by itself is divide both sides by the sine of 34 degrees, and that should give me my length of side x. So I'm just going to go ahead and type that in my calculator, and that's 10 times the sine of 52 divided by the sine of 34 degrees. And I got 14.09, which rounded to the nearest tenth would be 14.1. So the missing side, x, is 14.1. So let's go ahead and try another one. So this time in the triangle, the side I'm looking for is across from a 119 degree angle. So I could say the sine of 119 over x. And then the other pair that I'm working with is the one that's the angle that's 21, and it's across. Oh, this is kind of hard to match up. Didn't draw that very well, but anyway, the one across from, in other words, the one that it doesn't touch, the one that's formed by the other two sides is 21 degrees, so that would equal the sine of 21 over 7. So again, solving these is the same. We're just going to do the cross products, see what turns out. So that gives me x times the sine of 21 equals 7 times the sine of, oops, I'm running out of space. Okay, there we go, equals 7 times the sine of 119. And so then all I have to do to solve is divide both sides by whatever's with x. In this case, it's sine of 21 degrees. And that'll tell me what the length of that missing side is. And again, we just have to go to our calculator. 7 times the sine of 119. And then we're just going to divide by the sine of 21. And that turns out to be about 17.08, so it's about 17.1 is the value of x, approximately. Okay, so it's about time for a couple U-tries. I would like to kind of help you set up number 3 because it is a little bit different than the other two that we've done so far, and that's because, as I said before, we want to be able to match up the angle and the side it's across from it. So I can do that pretty easily with the pair that I know both of. I mean, I've got the sine of 64 and 32 are going to go together. But this time, oops, sine of 64 and the side across from it is 32. But then this time, this angle that I'm trying to, or the side that I'm trying to find is across from an angle that's not listed. It's not given in the drawing. But you can see that you know the other two angles in the triangle. And so we know that 3 angles in the triangle add up to 180. So just go ahead and find that missing angle and then give that one a try. And then go ahead and try number 4 as well. So we'll designate these both as U-try questions. So pause the video now. You can test yourself, tune back in, and see how you did. right, so thanks for giving those a try. X is about 33.7 in number 3, and it's about 36.8 in number 4. Now here's the setup for questions 5 to 6. Kevin, Adam, and Dan are passing a hockey puck. How far is Kevin from Adam? So let's see, Kevin from Adam, here's Kevin and here's Adam, and so in other words, we're trying to find the length of that side. So first of all, we have to see, is law of sines possible? Now obviously this lesson is about the law of sines, but eventually we'll learn another law if we can't use law of sines. And so we have to know how to identify when we can use this and when we got to go to this backup plan we're going to learn in the next lesson. So I've got this pair that I know both of, and so that means I can do law of sines. And so I know that the sine of 86 degrees over 25 has to equal, well, let's see. I want to find this length right here. Let's say I call this x, so I need to know this angle across from it. And so I'm going to have to figure out that missing angle, which is 23 degrees. And so now I can complete my law of sines proportion, which so it equals the sine of 23 degrees over what side I'm looking for, which is called x, and the x represents the distance from Adam to Kevin. And so again, doing the cross product is going to look like this: 25 times the sine of 23 degrees, and that's going to equal x times the sine of 86 degrees. And that means we're going to have to solve by dividing both sides by the sine of 86. And putting that in my calculator gives me, let's see, so that's 9.8 feet. So Adam and Kevin must be 9.8 feet away. So for part B, or for number 6, I guess, it's kind of part B of that question, we're going to leave that one as a you try. And I want you to pause the video and see if you can figure out how far Dan is from Kevin. So now I'm having you look for the distance between Dan and Kevin. So go ahead and pause the video and give law of sines a try again to find the distance between Dan and Kevin. And that one turns out to be about 23.7 feet. And that really does, I mean, there's no way to truly check it because these are not right triangles, so you can't check it using Pythagorean theorem, but it is a reasonable value because it's across from the biggest, or well, I guess the second biggest angle in the triangle. It's across from 71 degrees, and the side across from 86 is 25. So it seems reasonable that 23.7 feet could be across from 71 degrees. Okay, let's go ahead and turn the page. Okay, so far we've just been finding lengths in these triangles. And so you might be wondering, well, can you use the law of sines to find angles as well? Well, you absolutely can, but you have to be very careful when you do. So you'll notice this little caution here. It says, watch out. When finding angles, it is possible to have one solution, two solutions, or no solutions. This is called the ambiguous case. When we're finding an angle, it is possible for there to be two different angle measures that the missing angle that you're trying to find could be, or it's possible that the triangle won't it doesn't even make a triangle, so there is no possible way that it makes a triangle, so there's no solution, there's no way to find this missing angle because it's in a triangle that doesn't exist, if that makes sense. So again, that maybe is why they call that the ambiguous case. So as you know, that the word ambiguous, it actually is defined as open to more than one interpretation, or in other words, having a double meaning. That's one of the definitions. Or also unclear or inexact because a choice between alternatives has not been made. So both of those are the different definitions of ambiguous, and that's exactly what goes on when you're finding angles in a triangle. It could be a situation like that that's ambiguous. So here are some important facts to keep in mind. The sine function always has a range between -1 and 1. And think about that the sine itself really is defined to be in a right triangle comparing an opposite leg to a hypotenuse. And so that would be in a right triangle where the hypotenuse is the longest. And that would always be between -1 and 1, because you couldn't have a leg be bigger than the hypotenuse, so to give you a value greater than 1. And then we've seen with the unit circle that you could have negative values if you're in, different quadrants, where in other words, you had angles that were outside of what could be in a triangle. If the sine function is positive, then the angle can lie in either quadrant 1 or 2. So remember that when we looked at the unit circle, the sine was positive in the first and second quadrants. Remember, awesome students take calculus. So the sine, the SIN was positive in both the first and the second quadrants. To find the other possible angle, this is what we're going to do. So you'll use the law of sines, you'll find an angle, and if you want to find the other angle, you're just going to subtract the angle you found from 180 degrees. So the angles, these two possible angles you might get, are always going to be supplementary. The sum of angle measures in a triangle is also 180 degrees. And also, no triangle can have two obtuse angles. So that's one thing to keep in mind. That'll help us narrow down whether there's two possibilities or not, based on what other angles are already in the triangle. And the fact that you cannot have more than one obtuse angle in any given triangle, because that means it's already over 90 degrees. That means there must be less than 90 degrees to go around for the other two angles. So those are all things that are going to help us to figure out whether there's one, two, or no possible solutions. Just go ahead and jump in on number 7. So first of all, on number 7, we don't have a triangle to use as a reference. So it doesn't really matter what the triangle looks like. I'm just going to draw a triangle. It's obviously called ABC. So triangle, or angle A is 50. I'm going to put this one as angle A right here. It said side, so let's see if that's A. Let's say I call this B and this C. Again, I don't really know what this triangle looks like, but I do know that side AB was given as 4. Side BC, which is across from angle A, is 9, and they want me to find angle C, so they want me to find this. So setting up the law of sines would look like this. The sine of 50 over 9 must equal the sine of C over 4. So we've talked about how we use inverses for angles. So once we do the cross products here, then we know that the last step in order to find the angle will then be to take an inverse. So let's see, doing the cross products would look like this. It's going to be 4 times the sine of 50 equals 9 times the sine of C. So now if I go ahead and divide by 9 and get the sine of C by itself, let's see, divide by 9 on both sides. Then the final thing I would have to do in order to find my angle is I would have to get rid of the sine, which means I'm going to have to do the inverse sine. Now you can, as long as you use parentheses around this whole thing, you can do this all in one step in your calculator, making it more accurate. So I could just do the inverse sine of, let's see, so the inverse sine of 4 times the sine of 50 divided by 9. And that gives me about 19.9 degrees. So they wanted me to, I guess, did it say where to round to? We're just going to go with a 19.9 degrees. And then we got to see if it's possible for there to be another different angle. So let's see. If this one was 19.9, if one was 19.9, the other one would have to be, let's see, if I subtract that from 180, that would leave me with 160 degrees, actually 160.1 degrees. But if you look at that angle as a possibility, if you put it together with that 50, now you're over 180. So that means there's no way that this is a possible one. And this time there's only one possibility, because if you already have this 50-degree angle and the other angle is 160, you would already be over 200. It would be 210.1 degrees, and that's well beyond 180. So in this case, there's only one possibility. It's 19.9. Let's try another one. So this time, again, we have a triangle called ABC. So I'm just gonna, just for reference, draw this triangle. This time they give me an angle B that's 37 degrees. They give me, let's see, so side AB, I'm just going to call this A, and that one's B, and this is C. So AB is 47. That means this is the side next to the 37-degree angle. Side AC is 29, and I'm trying to find angle C. So there again, I've got the side across from the angle I'm looking to find. So I could say the sine of C over 47 is equal to the sine of 37 degrees over 29. Go ahead and do the cross product. So that's 47 times the sine of 37 degrees. Oops. 37 degrees. And then that's supposed to equal 29 times the sine of C. I'm sorry, my stylus is really acting up today. It's very messy. So divide by 29, and then of course we're going to take the inverse. So that's the final step. Once we do that, we're going to take the inverse sine of both sides. Technically on this right hand side it's not doing anything but canceling out the sine. Over here is where we're really getting doing the math. So taking the inverse sine of 47, inverse sine 47 times the sine of 37 divided by 29, all of that in parentheses together, taking the inverse of it, and I got 77.3 degrees. Now, if I were to find the supplement to that, in other words, subtract this one from 180, I'd get 102.7 degrees. Now let's see if that would work. Well, if I had 102.7, so 102.7 plus the 37-degree angle that I know for sure is in the triangle, that only adds up to 139.7, and so that still leaves me room for another angle in that triangle to be 40.3 degrees. And so in this situation, I really could have two possible answers. Both of these really make sense, and since we really don't know for certain whether this could have two possible different angles, we just have to kind of trust that, hey, well, we know both of these angles are bigger than 37 degrees, so they would work across from a side that's 47, which is longer than the one that's across from 37 degrees. So they're both reasonable, and they certainly could both work in this triangle. So this is where we say that it could be 77.3 degrees, or it could be 102.7. And this is that case where we have two, and the other one was where we just have one. Okay, so I'd like to do one more with you, see if we can find one with the third scenario, and then we'll leave the other three to be you tries. And if I recall, I believe that number 10 is the one that I wanted to go over. So, and the reason why that one really stood out to me is, and maybe you already noticed, that this one has a given angle that's quite a large angle. It's obtuse. And so I'm going to start off, I'm going to draw a triangle that maybe kind of want it to, if I can be sort of accurate. So I'm going to draw a triangle where I have an angle that's pretty big, that could, potentially be that obtuse angle there. And so this one's 114 degrees, and this is called angle A. And so when I pick the other vertices, A, B, and C, that means that the side AB, which is right next to the angle A, is 34 units long. BC, which is across from 114 degrees, is 12, and they want me to find angle C again. So I'm looking for this angle here, and this is the information that I have. So when I set up my proportion, my law of sines, I have the sine of 114 and over 12. And then the sine of C over 34. Doing the cross products would give me 12 times the sine of C equals 34 times the sine of 112. And, not 112, sorry, 114. I'd have to divide both sides by 12 now. And then, of course, I'm going to take the inverse. Oops, I didn't mean to do purple. I want to do red there. I guess it doesn't really matter. But just to be consistent what I've been doing. So if I divide by 12, and then, of course, I'm going to take the inverse sign to get my angle. And by doing that, let's see what I get. And when I tried to type that in, my calculator gave me this error message. It said quit and go to, or quit or go to, and it said value entered is not allowed in the function or command. And it said that the radian mode, and said like tangent pi over 2 and degree mode e to the, anyway, it gives us this basically an error code, which just says this value is outside of the domain of the sine function. And so right away, I know there's no solution here. There's no possibility that this is going to work. And so given these side links, and I mean, you can clearly tell if you just kind of use common sense. You've got this 114 degree angle. Across from it is the side that's 12 units long. And now we've got the side over here that's 34 units long. Of course, we'd have to have a significantly bigger angle across from it, and that's just not possible in a triangle that only adds up to 180 degrees. So we probably could have told right away, even just looking at this drawing, if we'd really thought about it, that this is going to be one of those that has no solutions. And that's why I chose this one to do. I could tell that by looking at those values already. So that actually does it for the law of sines. I would like you to go ahead and stop the video now, try the remaining questions as you try questions. This gives you a chance to kind of jump start before you get into the assignment. And you can tune back in if you want to pause it now. Try 9, 11, and 12, and then tune back in and check your answers before going on and completing the practice homework. So pause the video now, tune back in after you get done, and check your answers. 2, 9, 11, and 12. All right, so thanks for giving those a try. On number 9, the missing angle, there really was only one possibility because of the fact that if you got 41 degrees for angle B, that would work with the 75 degree angle. That would give you room for another angle to fit in the triangle for that third angle. But if you had the supplement to that, which is 139 degrees, that's too big to go along with 75, and then let alone have another angle there. So there's only one possibility on that one. On number 11, I'm sorry, I didn't mention this earlier. Hopefully you picked up on that. The angle that you had the information to find was angle C, but they actually ask you to find angle A. So once you find angle C, and you know there's two possibilities of 68.2 or 111.8, then you could find the possibilities for angle A by just taking the 47 degree angle that we knew for sure was in the triangle, and then those two possibilities, figure out what was left of 180 degrees. And then finally number 12 was not possible. So there again we ended up getting an angle that or a triangle that just doesn't make sense logically with how we know the structure of triangles to be. So that actually does it for today's lesson, and I hope you're well, and thanks for coming to class. We'll tune back in another day for the law of cosines.